Okay, to start our second segment, we've considering the case of a person carrying a briefcase. Of course, to carry the briefcase, you have to exert an upward force on the briefcase to keep it from falling. But ideally, there's no movement occurring vertically in the briefcase. I mean, it's, the normal person, they kind of bound up and down a little bit as they walk. So there actually would be some up and down movement in the briefcase as you walk along. But let's say an ideal case where a person just sort of glides along, maybe on roller skates or something, there's no up and down movement of the briefcase if the person is walking horizontally. And so the force that you're exerting upward on the briefcase is perpendicular to the direction of displacement of the briefcase. And so there should be no work done. And you can look at that with the equation for work equaling the magnitude of the force times the magnitude of the displacement times cosine theta. Well, it doesn't matter how much force it takes to lift the briefcase or how much displacement you carry it for, because the angle is 90 degrees and the cosine of 90 is 0. And so the work is 0. Now, of course, there is work done in carrying the case horizontally, but there's no work done in keeping it at a certain height. We can look in a little more detail also on the example of a person pushing a lawnmower. If you want to say calculate the work done by a person pushing a lawnmower if the force is constant at 75 newtons and the handle is at 35 degrees to the ground, and the mower is pushed 25 meters. Well, we have the equation like up here. It's just magnitude of the force times the magnitude of the displacement times cosine theta. Okay, so the force is 75 newtons. The distance is 25 meters, and cosine of theta is what takes care of the fact that the handle of the lawnmower is actually at an angle. And so if you're pushing this way on the mower, but the mower is actually moving that way, you want the x component of the force, and that's where the cosine theta comes in. 75 newtons times cosine 35, that's the x component of the force on the lawnmower, times the 25-meter displacement means that there were 1,536, joules of energy or work are done in order to move the lawnmower as that distance. And 1,536 might sound like a lot, but as I said, joules are really small. So that's not necessarily a whole lot of work. We weren't considering friction or anything like that. So, moving a lawnmower with no friction wouldn't really take very much work. There are, of course, other forces at work in pushing the lawnmower. When you are pushing the lawnmower, there's contact forces of the ground and the weight of the mower. The contact force of the ground that's related to weight would be the normal force. So you've got, again, the weight of the lawnmower pushing down and the normal force of the ground pushing back up on the lawnmower. But there's no movement of the lawnmower up or down. And that means that any displacement of the lawnmower is perpendicular to the weight and the normal force. And so no work is done by those forces. And so, the work done by the normal force, for instance, would be the force, that is the normal force in this case, times dr, or that would be, in other words, the magnitude of the normal force times the magnitude of the displacement, which we're calling r in this example, times the angle between the force and the displacement, which is 90. And again, cosine of 90 is 0, so it's all 0. There's also friction, of course, and we didn't consider friction in that example because that makes things a lot simpler, but there is friction, and that's a contact force that's parallel to the surface, or in other words, parallel to the direction of displacement, but opposite to the direction of displacement. because friction always opposes movement or potential movement. So the work done by kinetic friction in this case would be negative because you did positive work pushing the lawnmower forward. Friction is trying to go in the opposite direction, so that would be considered negative work. If the force of kinetic friction is constant, the work done by it could be calculated as WFK, that is work due to the force of friction, or done by the force of friction, would be the integral from A to B of the force times dr, or in this case, the force is the force of kinetic friction. Since that's a constant, you can take it outside the integral. So that would be negative Fk times the integral of dr. And in other words, that's negative Fk times L from A to B, L in this case being the path length, or the distance essentially from A to B. And so that would be the work due to static friction, or kinetic friction rather. Right there. The work done against the force is the negative of the work done by a force, and vice versa. Okay, so you can do, work can be done by a force, or work can be done on a force. And those two would be, or say against a force. Those two would be of the same magnitude, but they would be in opposite directions. And so one would be negative and one would be positive. So you could say that dW, that is the increment of work done by a force, is equal to the negative of the increment of work done against a force. You've got friction pushing this way, and so that would be negative. And to overcome it, you have to do positive work in this direction. Okay, so work done against a force is just the work that's required to overcome it. So you'd have to match the magnitude of the force, but in the opposite direction. And so again, one is positive and one is negative. Static friction can do work that's either positive or negative. An example of static friction doing positive work is the static friction that the tires on your car have against the road, or the road has against your tires, I guess you'd probably want to say. It's because it's that static friction that causes the car to move forward. So that in that case, friction is doing positive work. On the other hand, you have a certain amount of friction, for instance, by air on the car. And that is pushing the car back. And so that would be against the forward motion, and that would be considered static friction doing negative work. Okay. So an example of calculating friction when something's in motion, or calculating the amount of force required to overcome friction, rather, when something's in motion, would be moving a couch. Say if you want to move a couch on a level floor, the normal force on the couch is 1 kilonewton, in other words, 1,000 newtons. And the coefficient of kinetic friction of the couch on the wooden floor is 0.6. So in part A, what you do is you push the couch 3 meters parallel to a wall, and then 1 meter perpendicular to the wall. And that is going from point A to point B. So here on this little diagram, you've pushed it 3 meters this way, and then 1 meter perpendicular to that this way, and that goes from A to B. So 3 meters and 1 meter and a right angle between them. Okay, so the question is, how much work is done by the frictional force? So the frictional force, again, is just the coefficient of kinetic friction times the normal force, and that's 0.6 times 1,000 newtons, or 600 newtons. Okay, the work done by that frictional force would be Fd. So work done by friction, or W sub F, equals negative Fk, that is the force due to kinetic friction, times the distance that the couch was moved. So that's negative 600 newtons times 3 meters plus 1 meter, which is 4 meters, gives you negative 2,400 joules of work that's done by the frictional force. It's negative because it's against the direction of motion. And that's also how much work you would have to do just to overcome friction. It would be positive 2,400 joules. 2,400 joules could also be written as negative 2.4 kilojoules. All right, then part B says, you then decide you don't like where the couch is and you want to push it back to where it was, but you decide to push it in a straight line at this point because you're tired and you don't want to go back by the same route. So you just take a straight line back. And that goes from B back to A. And what is the total work done against friction in the entire round trip? Okay. Okay, so the work total would be the force of kinetic friction times the total distance that the couch has traveled. The couch, we know, traveled 3 meters one way and then 1 meter perpendicular to that, but we now need to know how far it is going directly from B to A. Since this is a right triangle, we can use the Pythagorean theorem to come up with the length directly from B to A, and that is just C squared equals A squared plus B squared. That is, the hypotenuse is equal to a side squared plus, hypotenuse squared is equal to side squared plus side squared. Or in other words, the hypotenuse is the square root of the two sides squared. So in this case, the distance directly from B to A is the square root of 3 squared plus 1 squared. That's the square root of 10, which is 3.16. So the total work done against kinetic friction for the entire round trip would be the force of kinetic friction, which is 600 newtons, which we got up in part A, times the total distance, which is 3 plus 1 plus 3.16. And that's 7.16. And 600 times that is 4,296 joules. So that's the amount of work you had to, or that basically, let me see how it asks the question in. Oh yeah, okay. In this case, notice how the wording goes. What is the total work done against friction in the round trip? That's why there's no negative sign here, because this is the work you're doing to overcome friction. If it were the total work done by friction, then friction is going against the direction of travel, so there would be a negative sign here, and it would be negative 4,296 joules. But because it's the work you're doing, then you're pushing in the direction, the same direction as travel, and that is the reason that there's no negative sign, it's positive. You notice that the total displacement of the couch is 0, because displacement is just, again, measured as the straight line distance between where you end up and where you started. In this case, you end up right back in the same exact spot that you started. And so the total displacement is 0, but the total work is not 0. And that's because work and displacement, even though they're both vectors, they don't necessarily behave the same way. The reason here is because of friction. Friction is what's known as a dissipative force, or a non-conservative force, meaning that friction is not conserved, whereas work and energy are conserved. Or, sorry, so basically, if you come back to where you started, your displacement is 0, but your work is not. And that's because friction basically acts no matter which direction you're headed in. And so you don't lose friction if you move backwards, is kind of what I'm saying. If you move backwards, you're losing displacement, but you don't lose friction. Friction is still there. And so because of that, displacement is 0 if you end up back where you started, but the work will not be 0. You're not saving work by moving the couch back to where it came from. You're expending more work. Okay, work done by gravity now. Work can be done by gravity, even though if the motion is horizontal, then normally there's no work being done by gravity. And again, that's because there's no work being done if the direction of movement is perpendicular to the force. And that's basically what happens with gravity if there's horizontal movement. The work done by gravity can be calculated as, sorry, forgot to put the arrowhead on there. Work times dot dr, and that is the magnitude of the work times the magnitude of the displacement times cosine, or sorry, that's weight, not work. They really should come up with different letters for these. Yeah, sorry. So the work done by gravity is going to be the weight times the displacement. And that's equivalent to the magnitude of the weight times the magnitude of the displacement times cosine theta. Weight is mass times gravity. So that can also be written as mass times gravity times displacement times cosine theta. Again, though, if the motion is horizontal, then work due to gravity ends up being 0, because cosine of theta would be 90 and cosine of 90 is 0. Okay, you can also work with components when doing this, the x and y and z components. In the usual coordinate system, the gravitational force would be in the y direction, and we would call the weight negative mg because it's downward, times unit vector j, because unit vector j is in the y direction. The work done by gravity over the path from A to B would be equal to negative mg times unit vector j dot displacement at point B minus displacement at point A, which is just the same as mg times the y coordinate at point B minus the y coordinate at point A. So if the motion is horizontal, that is no change in the y direction, then the work due to gravity is 0, because yb minus ya would be 0. So again, if the motion is horizontal and horizontal only, then gravity does no work. But if there is motion in the up-down direction, then there will be work done by gravity. If the object moves upwards, then the work due to gravity is less than 0, in other words, negative. Or in other words, you have to do positive work against gravity in order to raise an object. And if the object moves downward, then the work due to gravity would be greater than 0, or in other words, positive. Okay. An example of calculating kinetic energies and the energies in displacing something from one place to another is if you take a 20 Newton library book and move it down by 1 meter from a shelf to, say, a comfortable carrying position, and carry it 3 meters horizontally to a table. You might wonder, how much work does gravity do on the book? Well, we come to the equation, work due to gravity is equal to negative mg times the change in position in the y direction. And as it just so happens, what you're actually calculating here is the change in potential energy. Because there are actually, and this gets a little bit into what we are, well, what comes in the next chapter. We won't have time to do much of anything on the next chapter, but since it's effectively being covered here, I might as well mention that fact. Okay, so potential energy is energy that's due to an object's position or its condition or its composition. There are several types of potential energy. And the most commonly dealt with type is gravitational potential energy. Gravitational potential energy is potential energy that something has due to its height above ground. And that's because, of course, gravity is trying to pull it downward. So if something is able to remain a certain distance above the ground, then that gives it a certain amount of energy. And it's called potential energy because it's energy that's not being expressed right at the moment, but it could be. And when we say that it's being expressed, generally we mean that, you know, energy being expressed brings about some sort of change, like movement, for instance. So something that's like a library book sitting on a high shelf, the fact that it's being stationary up there on that high shelf, well above the ground, gives it a lot of potential energy. That potential energy could express itself at some point in the future through motion. Say if the book falls off the shelf, that would be kinetic energy. And what we say when we mean, or what we mean when we say that energy is conserved, is just that the total amount of energy in the universe remains the same, but energy can be changed from one form to another or transferred from one place to another. So when that book is sitting up on the shelf and it has a large amount of potential energy, it can then fall off the shelf and fall to the floor, and it will have a lower amount of potential energy when it hits the floor because it's at a lower height. The difference between the potential energy when it was up on the shelf and the potential energy when it hits the floor will be the amount of kinetic energy it had between those 2 points. So potential energy is converted to kinetic energy and is converted back to potential energy. But everything remains equal, or the total amount of energy remains the same. And gravitational potential energy, again, is what it has because it's a certain height above the ground, or technically the center of the earth, because gravity pulls from the center of the earth. But we use the ground as a handy reference just because we don't want to measure all the way down to the center of the earth, and things usually stop falling when they hit the ground. And gravitational potential energy is given by the formula mgh, or weight times height. Mg being weight, mass times gravity times height. If you look at the units, mass, of course, is in kilograms. Gravity is in meters per second squared, and height would be in units of meters. And when you combine these together, you get kilograms, meters second per, meters squared per second squared, and that is a joule. So the units for potential energy would also be in joules as your standard SI unit. That's the main type of potential energy that we're going to be concerned about here, because it's the type that's easily converted back and forth between potential energy and kinetic energy. But there's also other types of potential energy Like, for instance, the kind as a chemist that I'm more familiar with is chemical energy. And that's energy that's stored in chemical bonds within compounds. It takes a certain amount of energy to break a chemical bond, but when you break it, you get out a certain amount of energy. Or when you form a new bond, rather, you get out a certain amount of energy. Okay, so anyway, that's what I was getting at in this problem here. Notice that the work due to gravity is defined here as mg times the change in position in the vertical direction. That's just another way of saying mgh, or mg change in h anyway. So that is essentially, when you're asking how much work does gravity do on the book, you're actually basically asking what is its potential energy when it sits there on the shelf versus when it's coming down to where the level at which you're carrying it. Okay, so the potential energy, or the work done by gravity in lowering the book, is 20 joules. Or in other words, its potential energy changes by 20 joules. And it doesn't ask you this, but if you were asked to calculate the kinetic energy that the book had while you were moving it from the shelf down to the level at which you're carrying it, the answer would be 20 joules. Because again, energy is conserved. It can't just be created or destroyed. It can't come out of nowhere. It can't disappear into thin air. It can change in form, and it can go from one place to another, but it still exists, and the total amount in the universe remains the same. Okay, B is the work done by gravity while the book is being carried horizontally. Now again, when you see the word work, gravity, and horizontally, your first guess should probably be that it's probably going to be 0. And sure enough, if you say the work due to gravity between points A and B is negative mg times the height, basically that's what we mean by the y position, height at point B minus the height at point A. Well, if you're carrying the book horizontally, YB and YA are the same. Or the way we've drawn things here, basically 0 and 0. So negative mg, that's the weight, so that would be 20 newtons times 0 minus 0 is 0. And so we were right. Work by gravity is indeed 0 when something moves horizontally. Okay, so, and also the total work done against gravity is 0 if the path is closed. In other words, if the displacement is 0. It wasn't in this case here, but it was in the case of the couch. But of course, the work due to gravity there was 0 anyway, because it's not changing height. And what this tells you, though, is that gravity is a conservative force. So it does allow conservation of work or conservation of energy if gravity is involved. Okay, that is actually a little long for this segment, so I guess I kind of canceled any benefit to stopping short on the last one. But anyway, I'll call that here, and we'll come back with the third segment in just a moment.